Time travel used to be a taboo, relegated to the realm of science fiction. But a closet fraternity fell in love with this notion.
That's our dirty little secret. We physicists write articles on time travel, but we don't say time machines. We use a code word.
By day, illustrious scientists proved their mettle. By night, imaginations ran wild.
There was a young lady named Bright
who could travel much faster than light.
She set off one day in a relative way
and came back the previous night.
Their quest to build a time machine is about to come of age. Ever since Ron Mallett was a boy, he has harbored a dream of building a time machine. Today, he is professor of physics at the University of Connecticut and ready to share his secret with the world.
It's really such a powerful feeling to know that we're actually being able to manipulate space and time. And it's exciting because this shows that we may be able to control time, and that means that ultimately we may be able to control our destiny in a way that mankind never has been able to before.
Mallett's motivation began when his father died suddenly of a heart attack. Just 10 years old at the time and totally devastated, Mallett made a pledge.
If I could build a time machine, then I could go back and see him again and maybe save his life.
For almost half a century, and like many other scientists, he has conducted his research in closed laboratories.
It's only been since my own breakthrough at the end of the 20th century that I finally allowed myself to come out of the time travel closet, so to speak.
If he's right, the 21st century will see time travel make the leap from theory to reality.
It's refreshing now that in the 21st century we can explore this openly without looking over your shoulder like, when the guys in white coats are going to come and, grab us because we're talking about time travel.
Like all would-be time travelers, Ron Mallett had to find a way to understand time before he could attempt to travel through it. Leading theoretical physicist Michio Kaku has spent a career analyzing time. He believes a working time machine is inevitable.
In the last decade or so, there's been an avalanche, an electricity, an excitement about time travel. Historically, we physicists would pick up the topic.
Most of us think we understand what time is, but many of us are wrong. When we look up at the sun, we're actually seeing how the sun shone 8 minutes ago, because it takes 8 minutes for the sun's light to travel the 148 million kilometers to reach Earth. So we're seeing into the sun's past. Kaku believes that to master time travel, we need to understand time itself. He starts by correcting 3 important misconceptions.
The first misconception about time is that there's a universal now. That if it's 12 o'clock here, it must be 12 o'clock on the moon, and by golly, it must be 12 o'clock throughout the entire universe. Actually, in reality, it is impossible to synchronize your watches throughout the universe.
This is because of misconception number 2. Many people believe that time passes at a constant rate.
People also believe that time ticks uniformly throughout the universe. Actually, that's not true. You can show that in outer space, a clock actually ticks slower than on the Earth.
In fact, our satellite navigation systems only work because the US military make corrective adjustments to the satellite clocks every single day. Time is not absolute. It ticks at different rates in different places. The time traveler must cast aside any notion of mechanical time. And embrace the idea of time as a dimension. Misconception number 3.
Most people assume that we live in a three-dimensional world. Actually, we live in a four-dimensional world, 3 dimensions of space and 1 dimension of time.
Thinking of time as a dimension might not come naturally to us, but Kaku has a way of helping us. Computer games.
What is so fascinating about Pac-Man is that Pac-Man lives in 2 dimensions. He can only go forward, backward, left, right, but the concept of up is totally alien. They cannot visualize the concept of up. They live in a flatland. Now, we also live in a 3-dimensional world. We go forward, backward, left, right, up, down, but we are incapable of visualizing a higher dimension, a 4th dimension. That requires a leap of logic that our brain simply cannot comprehend.
Okay, I need to go to 5th Avenue and 33rd Street. Okay.
Just like Pac-Man, we use a 2-dimensional map to find a place on Earth. But unlike Pac-Man, we can leave the 2D flat world and go up into the 3rd dimensions of height. We also live in the 4th dimension of time. An appointment in our world might be in a building on a map and a floor in the building, but also at an agreed time. In fact, the 4th dimension of time is so interwoven with the other 3 dimensions of space that physicists now call the 4 dimensions together by one name: space-time.
We now believe that space and time are not invisible. They're actually a fabric that can be stretched, pulled, and perhaps even wrapped up into knots. If so, then perhaps the dream of time travel is not as preposterous as it sounds.
To build a time machine, we must find a way to manipulate this space-time fabric. Many scientists believe that it's this manipulation that will make time travel not only possible, but inevitable. We know how to change the speed we move as we rush along a busy sidewalk, but changing the rate we move through time is much more complicated. Most of us move forward in time at a rate of 1 second per second, but there are already time travelers among us.
Go for landing, over.
Astronauts on board the International Space Station have time traveled into the future. But how have they managed to do this? Space stations orbit the Earth at more than 27,000 kilometers per hour. Men and women have lived on them for more than 700 days. Upon their return, the astronauts had traveled a fraction of a second into the future. Their primary method? Speed. A spaceship is a time machine. The speed it travels at is slowing down time for the people on board. To demonstrate how motion can affect time, we must first appreciate that the speed of light acts as a cosmic speed limit. Nothing travels faster than it. This is a pulse laser. It measures one of the few absolute values in nature: the speed of light through empty space.
The beam comes through this series of lenses and mirrors. If we move that mirror back about a foot, then the light has to travel a further distance. And if I check this oscilloscope here, it tells me the extra time that the light has taken to cover this distance. So if we know the distance accurately and the time accurately, we can calculate the speed of light.
That speed is 300,000 kilometers per second. And experiments prove that this figure is constant across the universe. Because it never changes, it means that time can be manipulated. Physicist Jim Al-Khalili demonstrates that time can be stretched or squeezed. He uses a theoretical light clock located on the dashboard of his car. This device bounces a beam of light up and down inside the car, which is traveling close to the speed of light. The different way in which observers inside and outside of the car view this light beam demonstrates that they experience time at a different rate.
For me, travelling with the clock inside the car, I always see the light beam moving vertically straight up and down.
If Al-Khalili's twin brother watches from the roadside, he would see the light beam follow a different path. Combine this horizontal movement of the car with the vertical pulse of the light clock, and one thing results.
For me, standing watching the car go by, I see the light beam travel diagonally.
The distance light covers is greater for the viewer outside the car. But crucially, the speed of light is the same for both. Time equals distance divided by speed, so the time passed is less for the person who is traveling in the car. Time actually passes more slowly for the person who's traveling at speed. Scientists call this time dilation. Geneva, Switzerland. This is CERN, the European Organization for Nuclear Research, home of the world's largest particle accelerator. Scientists from 85 different nations study the subatomic world to understand how the universe works. At this space-age facility, they have been carrying out time travel experiments for more than 40 years. A useful time travel particle is the muon. Muons are high-energy particles produced by cosmic rays, which constantly bombard the Earth's atmosphere. Muons live for only about 1/1,000,000th of a second. Here in CERN, scientists use speed to make these subatomic particles live longer, thereby turning them into time travelers. Giant accelerators like this one at CERN push the muons to velocities approaching the speed of light.
If we have a muon traveling in a ring at close to the speed of light, its lifetime is prolonged. That means that the clock, which the muon is ticking slowly, slowly, slowly. So when the muon comes back, it has only gone through tick-tack, 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 while we have gone tick-tack, 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 tick-tack. So in a sense, the muon is coming to our future, because only 1 second has elapsed for the muon, 20 seconds have elapsed for us.
Scientists enable muons to time travel into the future by slowing down the rate of time for muon. There is, however, a catch, which is the major roadblock to using speed to build a time machine. any mass